Electronegativity and bond polarity. So showing the electrons as dots between two atoms is a drastic oversimplification, but a very useful one. The electrons are not always shared equally. In fact, they're often not shared equally. Just like, two people sleeping in a bed together, the covers are not shared equally, right? There's always one person that tends to pull all the covers over during the night. So that can happen with electrons as well. If we look at how hydrogen and fluorine share the pair of electrons between them in hydrogen fluoride, it looks more like this. The fluorine hogs the electrons. Big blanket hog. And the hydrogen lets her do it. What happens then is we have more electron density around the fluorine than around the hydrogen. And so that ends up giving the hydrogen a partial positive charge and the fluorine a partial negative charge. It's not a transfer of the electron. That would give us ions. It's just an unequal sharing. So this is the lowercase delta in the Greek alphabet. Delta plus, delta minus. That means a partial charge. Not plus one, minus one, but partial. And that it could vary. We don't actually care that much exactly what it is, but maybe it's plus 1/3 and minus 1/3. It's just a little bit. That causes one end of the ion of the molecule to be slightly charged. So if you have hydrogen fluoride molecules between two metal plates here, their orientations will be all random. If you put a charge on these plates so that there's an electric field here, and this is positively charged and that's negatively charged, the negative plate attracts the positive ends of the molecules and they'll all spin around like little compasses and they'll line up. It's crazy. So we can indicate that positive and negative ends with the deltas, or we can use the arrows. So my favorite analogy for this unequal sharing business is, again, the electrons are like little boys, and the nuclei are like the homes or the families, the moms. So hydrogen and fluorine each have an electron. They go out and play together. Whose house are they going to spend more time at? So hydrogen, they don't have cable or satellite or anything. They have a VCR and some Thomas the Tank Engine tapes. These kids are 12, okay? If you're hungry, mom's got some stale saltine crackers and you can have water out of the tap, right? The backyard is kind of overgrown. It's just not really all that attractive. Fluorine's house is a little bit different, okay? They've got this big screen TV. It's the size of the wall. They have all the pay channels. They have all the game systems. They have a soda fountain in the kitchen. I want one of those. It only has to have Diet Dr. Pepper, though. If you're hungry, Mom will call out for pizza, have it delivered. Where are those boys going to spend most of their time? At Fluorine's house. Why? It's cooler. It's more attractive, okay? So fluorine is more attractive to electrons in a bond than hydrogen is. And the arrow business, I think of, Dad's out in the front mowing the lawn, and somebody comes along, where's little boy fluorine? Where did those kids go? And he points. So the arrow points to the place that's more attractive to the electrons. And then we just put a little plus sign on the other end to make it not look like an arrow. I don't know. This is the positive end, and it points to the negative end. So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. So fluorine is the most electronegative element. It's the coolest house for little boy electrons to play at. Electronegativity is inversely related to atomic size. And so we see that the trend in electronegativity is exactly opposite to the trend in atomic size, except for the noble gases. So this is having to do with attraction in a chemical bond. Since the noble gases really don't react much at all, I mean, if you want to study noble gas compounds, you have to make a huge effort to make the noble gas compound to study. So most of us just ignore that as even happening. So we just leave them completely out of talking about electronegativity. So here's a cool three-dimensional graph. So you'll notice that group 8A is missing off the end here. That's intentional. It's like not worth talking about. Here's fluorine. So the taller the block, the more attractive to the electrons. Fluorine is the ultimate play place for the electrons. So it has been assigned an electronegativity value of 4.0. It's kind of like a grade point, right? 4.0. And everything else is marked relative to that. And so we see as you go across a period, atomic size decreases. Electronegativity increases. As you go down a group, atomic size increases, electronegativity decreases. And that goes back to what we talked about with the lattice energies and the atomic, the ionic radius. If those ions can get closer together, they're going to be more attracted. And so when you've got really big, bulky atoms in the covalent bond, they're not as attractive to the electrons as if they're smaller. So for electronegativity, I basically just think of, okay, fluorine's the ultimate, and whichever, if you're comparing two, whichever's closer to fluorine is going to be more electronegative. You can do stuff with the actual numbers, and the numbers are all listed out here, and there'll probably be some homework problems that ask you to compare those. I'm not going to ask you to do anything with those numbers on a test, though, because we just need to understand the trend and relative electronegativity. You'll notice like carbon and sulfur have the same electronegativity. So if carbon and sulfur were sharing a pair of electrons, they would be equally attractive to the pair of electrons. And so it wouldn't get lopsided like that. When the electrons are not shared equally, we say it's a polar bond, because one end's different than the other. Our planet has a north pole and a south pole. It has to do with magnetic fields. They're different in terms of the magnetic field. In a polar bond, the ends are different in terms of the electron density. So we can measure that as the difference in electronegativity between those two atoms. And it's actually a continuum from no difference, and the biggest difference you can have is 3.3. There's everything possible in between. So arbitrarily, we make these distinctions. Around 0.4, we say if the difference is 0.4 or less, we'll call that a nonpolar bond. Your book uses the word pure. I think that's dumb. I like nonpolar. In between here, that's a polar bond. And if you get above 2.0, this is like the one, like with potassium and chlorine. It's not that potassium's little boy is just playing at chlorine's house a lot. The chlorine actually adopted him, right? So it was transferred. That's an ionic bond. That's just an extreme of the sharing, really. So there's this continuum, and we talk about ionic bonds or polar bonds, but actually this is just an extreme version of a covalent bond. Electrons are transferred.
And since the kid is over Chlorine's house, mom's like, I don't feel very.
Yeah, exactly. So, that little boy is now officially adopted by chloride, but his mom still wants to see him occasionally, right? And so there's this attraction, and they're going to keep in touch. And actually, I was thinking about this yesterday. I didn't have time to actually investigate this, so I'll investigate it here right now, and we'll see how it goes. So if you think about parents getting divorced, okay, and the one parent gets custody, right? Well, sometimes there's joint custody, and sometimes there's one gets sole custody. So the ionic bond would be, mom has sole custody of the kids. Dad's going to maybe be nearby and want to see those kids go to their baseball games, etc., but he doesn't have any custody of them. In this nonpolar bond, in the polar bond in the middle, mom's got more custody than the dad does, right? So he maybe has them on alternate weekends, but most of the time they're at mom's house. I'm actually liking this. And this is equally shared custody, which gets really, really complicated for the kids, but whatever. Another way to measure bond polarity is called a dipole moment. It's given the symbol mu. We're going to talk about it. We're not going to do much with it. But a dipole moment happens whenever you have a separation of positive and negative charge. Opposite charges do not like to be separated. And so there's a tension there. There's an increase in potential energy. The dipole moment is Q, the charge magnitude, times R, the distance between the separated charges. A common unit is the debye, which is actually a Coulomb times meter. There's the value. I'm not going to do anything with that on a test either. We look here at the dipole moments of several molecules. Here's chlorine, Cl2. So we think about this. Well, two chlorine atoms, the atoms are the same element. They're going to have the same electronegativity. So without looking at numbers or anything, we predict that this is going to be a nonpolar bond. It's going to be shared equally. And we look at the difference in electronegativity, it's 0. The dipole moment is also 0. ClF. So here we've got chlorine and fluorine. And the fluorine is more attractive to the electrons. And so we should predict that this is going to be a polar bond. And we see that there's a difference in electronegativity, and this is the measured dipole moment. The dipole moment follows the same trend as the difference. See, I see delta, I see change. Difference in electronegativity, but there's not a direct correlation or anything. And here's lithium fluoride. Lithium being a cation, a metal cation, and fluoride being an anion. So here, the difference in electronegativity is very great, and so the electron has been transferred to the fluorine, and the dipole moment is much higher. Can't remember what's next. I don't want to talk about that yet. So this can all be quantified, and I want you to be aware of that, but this is what I really want you to be able to do. Not like that. There's polar bonds, and there's nonpolar bonds, and there are ionic bonds. And you should be able to predict what kind of a bond it is just using the periodic table. So this is how you do it. Ionic bond, if you have a metal and a nonmetal. So metal and nonmetal, ionic bond. We already learned that, so that's just something you already knew. A nonpolar bond, two identical atoms. So hydrogen, H2, that's going to be nonpolar because it's two hydrogen atoms. They're the same. And then polar, two different nonmetals. Now this one does not work 100% of the time, but it works most of the time, and for a lot of things that's good enough. So looking at these then, ClF, HF, because there are two different nonmetals in this molecule, we should predict that those are polar bonds. Like I pointed out earlier, carbon and sulfur have the same electronegativity. So a carbon-sulfur bond is actually a nonpolar bond. So that's one example of where this generalization doesn't work. But it's not going to come up very much. Any questions about that? Another way we can look at this is percent ionic character. And that's defined as the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was completely transferred. So we talk about ionic compounds as the electron being transferred from one to the other, never coming back, never coming back to visit or anything. That's not actually true. There's none that are 100% ionic. but they are so high that practically it doesn't matter. So here we're looking at percent ionic character, which ranges from 0 to 100, versus electronegativity difference. So the greater the electronegativity difference, the greater we would predict the percent ionic character to be. So electronegativity difference is not the only story. The distance, the sizes also matter. So what we see is we've got clusters. There's this cluster up here, and there's a cluster down here. So these are all these are all nonmetals, right? Iodine and bromine, hydrogen and iodine. And so they all have low percent ionic character. Using my simplified rules, we would look at these and say, those are polar, but they're going to be covalent, right? Because they're nonmetals. We say it's ionic, an ionic compound, if we get above 50% ionic character. So if we look at this cluster up here, here's HF. HF isn't an ionic compound. It's up here in the cluster, but look, it's below the 50%. So we'd say, well, yeah, that's polar, but it's not ionic. And all of these guys up here are a metal and a nonmetal. So my rules still work up there. Any questions? So this is what we should be able to do. Classify these. I should really just change the slide. Not pure, we're going to call that nonpolar. Nonpolar covalent, polar covalent, or ionic. So bond between iodine and iodine. Nonpolar covalent, right? They're the same. So nonpolar. How about between cesium and bromine? Ionic. We have a metal and a nonmetal. So that's an ionic bond. How about between phosphorus and oxygen? Polar. Any questions? This is really important, being able to identify polarity. A lot of you are going to go on and take organic chemistry, and this is one of those things that's really important in organic chemistry.